So Morteza Kazimapur is a senior platform engineer with 10 plus years experience building fault-tolerant cloud-native infra for large-scale ML and data platforms. He specializes in Kubernetes, AWS, and open source tools with a passion for optimizing GPU workloads and empowering teams through automation and mentorship. And I will say this is quite unique because this is we've had 3 talks from American hyperscalers, so Pinterest, Lyft, and Uber. And it's great to have I think it's the first time we've had a European, let's call it, large scale engineering organization doing AI at scale. So it's great to have Zalando here. Over to you, Morteza. We can see your screen. Everything's looking good.
Thanks, Jim. Thanks for having me. My name is Morteza Qassembur. As Jim said, I work as a senior platform engineer in team machine learning infrastructure at Zalando. Today, we will be talking about the platform engineering aspect of FeatureServe, how we implemented Hopsworks FeatureServe as our centralized real-time online FeatureServe at Zalando's scale. For those who are not familiar with our scale, Zalando is Europe's largest online fashion platform, operating over 25 countries and serving over 50 million customers. So we're using Hopsworks as a feature set to support our real-time AI use cases, such as personalized recommendations. And in this talk, I will be focusing on the systems aspects of operating features at a larger scale. This involves challenges that we face in terms of availability, decreasing the blast radius in case of incidents, and also minimizing latencies for low latency requirements. So yeah, without further ado, let's go to the next slide. Zalando central feature search. So why is it a central feature search? Why should it be centralized versus like it could have just many feature search distributed across the teams and organizations? So the idea is to have one centralized platform to reduce the data silos and to increase the consistency, like for training and production across multiple teams and departments. This will allow higher collaboration and more visibility into the features, the versionings, and also it provides reusability for the features by making the features more discoverable. Another reason to make it centralized is so we can have a team that has experience in administrating these systems in a larger scale and can ensure that the uptime and latency is optimal. This is crucial for low latency real-time services. What is the system's operational requirement that we have? Because we're looking at FeatureServe as a platform view. First of all, SLO, low latency for online investor is a crucial KPI. We are expecting less than 10 milliseconds for some of our use cases, although not all of the use cases involve that low latency, but still a lot of use cases that especially involves customer facing applications, it requires low latency. And another one is high availability, because of course, if there is an outage, you could fall back to a backup system, but still we want to ensure that we were running on high availability, 99.99 availability. This means less than 4 minutes outage in a month, or in a quarter around 30 minutes, which is if we can achieve it, I think it's impressive. To achieve that, we needed to make sure, by the way, the items that I've marked as green is the ones that Hopsworks feature store already provided to us. So to ensure that we achieve the high availability, we need to make sure that the data is replicated across multiple availability zones. And the flash radius for the project means that we need to support multi-cluster setups for different projects. Although there are projects that could use shared environment, but some of the systems require dedicated resources, and because their use case is highly critical, and we need to make sure that they are always running regardless of any other system making noises for them. So noise and error issue, we don't want that. Scalability is, of course, always a challenge, but a bit, especially with the database. But with Hopsworks choice of database, which is on DB, it was pretty impressive, like how it can handle. First of all, it can handle the response time and how it is scaled. So for run DBs, one of the components for the database is RDRS, which is run DB REST API server, and another one is a MySQL font for the it's kind of like MySQL and then DB. And the other one, which is still one of our concerns, is the event bus. So for Kafka as the event bus, in the version 0.9, we don't have the desired scalability at the moment. It's limited to 3 workers per cluster, but this will be changed. I will explain to you in the next slides how. And compatibility with the Zalando stack, providing managed cluster API for us so we can implement infrastructure as a code. High feature firstness, which means like the rise should be first done in the online store, then on the offline store. So it's very important for us that we can serve fresh features to provide more accurate and better personalization items. And integrated features, vector database, which I think this is already talked about already in this type. It was one of the requirements that some of our stakeholders required. And last but not least is like providing versioning and also monitoring in the features, which is already inbuilt within the Hopsworks features, which was great. So let me explain a bit about how we implemented infrastructure as a code part, because this is the part that is shared between both implementations that we have. I forgot to mention that we had 2 implementations in Zalando. One was on EC2 instances, the other one was in EKS. So we are trying to like show like what was the challenges between both of them. So we use the Hopsworks API, deployment API, to deploy resources in AWS accounts. That means that we can we can ensure the consistency and reproduce the same results by deploying the same configuration in different environments, in the staging environment, in production environment. We can test things in staging first and then ship it to production. We can have better control on the versions of the package and like the cluster version and everything. And the most important thing for us is like the visibility into how the platform is deployed. Like if you want to see like what's the current version of like a certain image or a certain package in the cluster, you don't have like a session with services, a digging run. You could just look into the GitHub and understand what's happening. So to achieve that, we have this hybrid setup for the CDP pipeline that involves the dependency services that we deployed. Like this includes but not limited to VPC endpoints, for example, which enables the network connectivity, the S3 buckets, the IAM roles. And the part which Hopsworks is taking care of is like to deploy the AKS cluster itself, and also then deploy the Kubernetes resources that is required for Hopsworks switches to run. It involves like deployments, replica sets, and etc. But remember when we said that we need the feature source to be resilient, and it needs to be like has a reduced effect, like it needs to be like isolated. Each project needs to has an isolated cluster, so the blast radius should be reduced. What does that mean? Like in Zalando, we have certain network topology. Like each team has its own VPC and it's running on separate AWS account. So, and we need to, first of all, we need to make the connectivity possible in using some VPC peering system that you can see in the picture. And then we have the concepts of like the federated feature source here, which is like separated clusters running for different projects. So for example, cluster A here is a dedicated project, a dedicated cluster for projects for team A, and team B can has its own dedicated cluster, and then they could have a shared environment that you could use the most frequent features that feature groups that could be shared across teams and across departments. But this is not as easy as just deploying multiple feature sources. The metadata for and information for this should be consolidated and aggregated into one metadata store for access control, for like managing the team members, and also to store them as features in an offline bucket that can be retrieved later on. So this feature is already provided to us by Hopsworks Feature Suite. We are already utilizing this. This is great. This is I think this is a great solution that we achieved, and it enables collaboration between teams and organizations a lot while ensuring the availability and resilience of the design. So our first implementation was like with the version 3.9, and it was on EC2 instance. On EC2 instances, we had, what does that mean? This means that a bit same separate AWS accounts that you saw in the previous slide. Now you can also see them here. But this is a simplified architecture diagram. By the way, it doesn't involve all the components, but it zooms in a bit into the EC2 instances part that you will see. Like we have separate nodes for MySQL Server, for NDB data node, for NDB management node, and for the head nodes, which runs a bunch of services like Console, Kafka, Online FS API, and etc. So this is a good design because all the instances are replicated. They are available within different availability zones, which is something that we wanted, and provides acceptable level of service isolation between the EC2 instances and the nodes. But if you see here in the whole head node is quite busy. It's running a lot of services, which was one of the main challenges that we had actually with this setup. So let me expand on that. Availability and reliability on the head, especially on the head node, was a problem because a lot of processes were running and competing for the same shared resource, especially on the memory, and it could often lead to out-of-memory situations. For example, monitoring services such as Logstash and Prometheus could easily bring the whole node down by consuming more resources than expected, which could be partially preventable by setting soft limits and hard limits into the processes itself, and like in the system level. Like for example, for Prometheus, you have this go mem limit option that we could set for Logstash, which is running on JVM machines. We could have JVM settings for like XMS or like garbage collection settings. And Also, there is possibility to use C group memory limits as a Linux facility to limit the process memory usage. But this was not implemented on the version 3.9. And while we POC it, the solution didn't face these issues. And later on, when we started onboarding use cases, when we faced this, already the version 4 was available, which was running on Kubernetes, which solved a lot of these issues. So we didn't invest a lot on fixing those issues on 3.net. Another issue worth mentioning is the redundancy part. So the blue VNC strategy was slow. And when there was a failure, it was very sluggish when like switching over to the secondary node, and not all the services were available actually on the secondary node. For example, Prometheus was one of them, if I remember correctly. So what is that? And then that was the availability issues, but then we also have like administrative issues, like not easy auto scaling, which involve like an which is very important actually. And high possibility of configuration drift. This means like if someone has a session to one machine and like change some configuration, we have no way of knowing that. And also the Linux administration overhead. Or why was there overhead there? Because EBS storages were just attached to the EC instances, and like, I mean, if you needed to like scale up the database, you also needed to scale up the storage. It was often easier to just SSH to the machine. First resize the EBS volume and then SSH to the machine and resize the file system. But compared to just spawning a new node, wait for the database to sync the whole data, because the data could be a lot. Like we are talking about like hundreds of gigabytes on sometimes terabytes of data. So it's just easier if you can just resize the file system. And the stack was not running on Kubernetes, which is not very nice because we were really used to running things on Kubernetes. And we like it that way in Zalando. So feature version 4.5, which is running on EKS, has solved a lot of these issues for us. This is how it looks like. It fixes the issues that we had with self-billing. Like if a service was restarting, like crashing, it would just the Kubernetes will just could restart it automatically for us. We didn't really need manual interventions, and more isolation on the container level, which is appreciated because, like, in example of Prometheus, for example, the Prometheus node, the Prometheus service itself was crashing, not the whole node and not the whole API endpoints and etc. So everything just working fine. Only the monitoring service is crashing, so we can take a look into it and fix it. Not a big deal. It doesn't affect the availability of the service. It doesn't affect users' ability to log into the UI, for example, because the UI was one of the services which was also running on the head node. And less risk for the configuration drift because everything is managing deployments, and then the deployments are, I mean, Kubernetes workloads could be replicas as well. They are deployed by Hopsworks API, of course, but then we are providing the schema to deploy those configurations, like in formats of like hand chart, which is very easy to keep track of and very good for visibility. And resource allocation to the projects after is easier to understand and manage, because now we are utilizing EKS node groups per clusters. This means like you could just see it in the UI without too much hassle, like how much users are attached to a certain cluster. And this has the benefit of like just doing a slow rollout of the new versions of the cluster, or just resizing the cluster size without being worried about like resizing the ABS volumes or restarting nodes, which is great. Like it's just a rolling update instead of the blue giving update. You could see here, there's a diagram here that explains like the network connectivity and stuff mostly, but the important part for me here is like how the things are deployed, especially in the MySQL, the 1DB, they are deployed with their cassettes, and they are controlled and scaled with Kubernetes horizontal product autoscaler, which is great. And for Kafka, the event bus, we also have Streamzy, which is the Kubernetes operator that it's deploying the cluster and managing it. That it also provides the facilities to implement auto scaling. This specific part we haven't implemented yet, but this was one of the big reasons that we switched to the new version, because we would like to utilize this as soon as possible. So yeah, auto scaling, as I mentioned. How is the auto scaling implemented right now is for 1DB, it's scaling up based on the response time of the service, because remember that we had like certain latency requirement for some projects. This means that if there is too many requests were coming to the same database instance and it's already slow, if we could just make it faster by spawning new replicas, and the new replicas are using the nodes available in the node pool, then automatically a new node is just found attached to the Kubernetes cluster and is being utilized by the 1DB instance. And it's very easy compared to the hassles that we had on with the EC2 instance system. In the EC2 setup, also there was a management UI and API that we could use to manually scale up the system, but that was manual, not very desired. So, and then another criteria for us is like requests per seconds per pause. Why does that matter? Because the API itself has accepted RPS, like like a tested number of RPS that it can handle. And if the RPS is too much, then we need more replicas, of course. And the same HPA is used also for CPU usage, because some of the queries could create a lot of CPU usage, and when you multiply by with the huge scale of queries that are coming to the database, of course, this could be a challenge. We also have it for some of the services at the moment, and I believe this could be expanded to a lot more, but I wanted to be accurate here, so I just mentioned the ones that are already there. And our flight service, Apache our flight service, for example, depending on the request queue size and time. And for Streamzy, which is a Kafka operator for Apache, we would like to see how it can scale up based on the using its facility called cruise control based on the load on the event bus. So this is my last slide. Yeah, time for questions.
Brilliant. Thanks, Mutez. And fascinating to see a lot of your challenges related to scaling data platforms and Kubernetes. It's not something that's as widely deployed for data platforms today as many may think. I'll take one of the questions from the Q&A. If we take Kubernetes versus EC2, do you see in terms of performance a difference or operational effort? Because often people think when you run data platforms on Kubernetes, you'll get a performance hit. And what about the operational effort of the relative two?
This is a very good question. We actually did a lot of benchmarks comparing two setups, EC2 and the Kubernetes setup. We didn't see any noticeable reduce in the performance, and for us, the reduced manual labor of maintaining EC2 instance, which was just lifted. Then when we just moved to Kubernetes setup was one of the biggest reasons, and also the scalability, as I mentioned, like auto scaling, this was one of the biggest reasons for us. But in terms of performance, we didn't see any noticeable overhead when switching to Kubernetes setup. It wasn't like to 20% drop in RPS or something like that. No, it was easily just achieving the same benchmarks that it was achieving in the EC2 setup.
That's reassuring to hear for all the Kubernetes data vendors out there. Thanks, Morteza, and I hope you'll be able to take questions on Slack if we're there. Is it okay to share your slides on Slack?
Yes, of course.
Great. So you can jump over to Slack, everyone, if you want to ask Morteza questions and check out slides.